So, you would recall that from the last lecture we already looked at unsigned integers and signed integers, and in this lecture we are going to take a closer look at the 2's complement representation, and in particular we are also going to look at how the magnitude of negative numbers in 2's complement representation can be computed. Okay. So, we discussed this last time that you can treat the most significant bit as the sign bit, so that if that bit is 1 then the number is negative, otherwise the number is positive, and this looks like a reasonable representation. This is also called the sign magnitude representation, and we had looked at this circle last time. So, these are the 8 combinations of 3 binary digits, and I have ordered them along the circle so that this is the representation of 0 as an unsigned integer, 1 as an unsigned integer, and so on. Okay? And as a sign magnitude representation, we saw that these 4 represent positive numbers, these 4 represent negative numbers. So that's exactly what they are, right? We didn't, I mean, this is a very easy representation, so there should not be any problem with it. We also saw last time that this basically gives rise to 2 increasing directions. You're increasing in this direction and also in this direction, and these are 2 opposite directions, right? And you have these 2 representations of 0. So, in order to motivate the 2's complement representation, we could ask this question that, well, the last representation we saw was okay, but it was a bit wasteful, and it had this, sort of undesirable thing that there are 2 increasing directions along this circle, right? So, we could ask, well, how else could we represent? And we'll say that let's still keep the MSB to represent the sign. That's a convenient way. Just 1 bit tells us what the sign is. But what about the magnitude? Once we know the sign, how do we find out the magnitude? If I just use the black bits, ignoring the sign bit, then I get these 2 representations of zeros, and I get 2 increasing directions, and all of those problems are there. So, could we avoid it? Now, if I am going to treat the MSB as the sign bit, then clearly these are going to be positive integers and these are going to be negative integers. And for the positive integers, it's kind of convenient to just read these off straight away as the unsigned representations would be, right? So, that is 0, 1, 2, 3. And these I know must be some negative integers, but the question is, what do I let this represent and what do I let this represent? Which negative integer should this represent and which negative integer should this represent, and so on. So, that is the question. I mean, it is clear that we want these to represent positive, these to represent negative. For the positive one, this is fairly clear. For the negative one, if I just take this as sign and this as the magnitude, then we have this problem, 2 representations of zeros, 2 increasing directions. So, can we sort of map these representations to negative integers such that we don't have 2 representations of zeros, such that we have 1 increasing direction around the circle, and so on. And so, what we are going to do is, we are going to think of this circle as a wrapped around number line, and we will try to see at what point can we break the circle and pull it out as a number line, right. So, where do we break the circle? So, clearly the logical points to break the circle are where the MSB is changing from 1 to 0, right. So, this is one logical point and this is the other logical point. Now, if I did break the circle there, then I would get a number line in which I know 0, 1, 2, 3 is increasing in this direction. So, my number line would look like this, 0, 1, 2, 3 increasing in this direction, and then I have these 4 binary sequences represented there, and I have to assign some negative numbers over there. The problem here is that clearly that 0, 1, 2, 3 has defined the direction in which the numbers are increasing, right. And so, anything that comes in this other part where I have not assigned any integers must therefore be greater than 3. So, really there is no space for negative integers here, right. So, therefore, let us look at the other alternative place for breaking the circle, which is the other place where the MSB changed from 0 to 1. And if I did that, then I would get a number line where the increasing direction is now like this. So, from 0, 0, 0 to 0, 1, 1, and this other part now is before this, right. Is this clear? And now, what is the increasing direction? That is clearly the increasing direction, 0, 1, 2, 3. And now, what we want to do is, we want to put negative integers over here such that there are no two representations of 0, the same increasing direction applies and all of that, right? So now it's clear what those negative numbers should be. Is that clear? Right? And now once I do that, this is consistent with the increasing direction, and now this basically gives you the mapping that we saw in the last class, that this represents -4, this represents -3, -2, -1. We get one sweep of increasing integers over here, and of course when we are going from +3 to -4, there is a wraparound. That's the place where the number line broke, right? That's the place where the circle broke and we pulled out the number line from there. Nice parts about this representation are there are all 8 numbers being represented, and there is no wasteful representation. 0 is not represented twice. Okay. So now the question is that, well, this looks okay, but now I need a way to figure out that if you give me 1, 1, 1, then I really mean -1. I mean the most significant bit does tell me that it's a negative number, but how do I figure out the magnitude? How do I figure out that the magnitude is 1 from there, right? Similarly, if I give you 1, 0, 1, I need to figure out that the magnitude of this is 3. The MSB tells me that it's a negative number, but how do I figure out the magnitude? So we need a way to sort of map from here to the magnitudes, right? Now let us see what this map is, what is our desirable map. So if I look at this 1, 1, this should map to the magnitude 1. If I look at these two bits representing the magnitude 1, 0, this should map to 2, 0, 1 should map to 3, and 0, 0 should map to 4. That is our desired mapping. Okay. The question is, can we come up with some closed form representation of this mapping? Can we come up with some function which, given the binary string, which will allow us to compute the magnitude? And it turns out that if you just look at this a little bit, spend 5 minutes looking at this, you'll see that there is a pattern over there. And one way of sort of looking at that pattern is that you look at 1, 1, this represents the unsigned integer 3, and the number that I wanted to represent is 4 minus 3. Okay? You look at 1, 0, which represents the unsigned integer 2, and the number that I wanted to map to is 4 minus 2. And similarly, 1 I wanted to map it to 3, and 0 I wanted to map it to 4. Right? Now, where did this 2 square come from? This is really the largest magnitude that I will be able to represent, right? Because I will get this number, which is 1, 0, 0. This will be a negative number. As an unsigned integer, this will be 0, and then it's some power of 2 minus 0. So that will be the largest magnitude. And we know that, in a number line like this, if there are 3 bits, I can represent 8 numbers. So +0 to +3 has taken up 4 of those positions on the number line. So the negative numbers will be -1 to -4. So the largest magnitude is 4. So that power is 2 squared over there. Right? So I'm sort of saying this in a slightly non-formal way, but if you just spend 5 or 10 minutes looking at it, you'll see exactly this is the pattern. Right? I mean, I want this to represent the largest magnitude, and that largest magnitude is 2 squared minus 4. This to represent 1 less. This to, I mean, if you look at it, this is just this black bits, it's increasing as 0, 1, 2, 3. And I want the magnitudes to reduce as 4, 3, 2, 1. So clearly there has to be a subtraction relation over there. Another way of looking at it is that you look at 1, 1, this represents the unsigned number 3. And to get this number 1, basically to implement that 2 squared minus 3, one way to implement it is to flip both these bits, get the decimal number 0, and then add 1 to it. Okay? And once again, you can convince yourself by looking at a few examples that this does exactly the same thing as subtracting the unsigned integer 3 from 2 squared. Right? And similarly for the other ones. If I take 1, 0, this represents unsigned 2. I want to subtract it from 2 squared. I could write down 2 squared minus 2 and do that, or I could flip the bits, find out the decimal number, add 1 to it. That will give you exactly the same answer. And this is not a coincidence, one can prove this. For example, you can use induction to prove this. So I could take the bits of magnitude, flip them, get the decimal number, add 1, and I'll get 2 squared minus whatever it was over here. Right? So these are two different ways of arriving at the magnitude of negative numbers. Both will give you exactly the same thing, both are doing exactly the same thing, just two different ways of doing this. So therefore, if I ask you to compute the magnitude of a negative number, so let us say 1, 0, 1, 1, 1, what do? We look at the MSB, immediately it's a negative number. And then to get the absolute value, you ignore the MSB. So you get 0, 1, 1, 1. Flip every bit here, you get 1, 0, 0, 0. That's decimal 8. Add 1 to it, you get 9. So the absolute value is 9. The original number was minus 9. Right? And the other way of doing it is look at the MSB, figure out that it's a negative integer. Then to find the absolute value, you ignore the MSB. Find out what the rest of the number represents as an unsigned integer. That's 7. Now you subtract 7 from a power of 2. What should be the power of 2 that you should subtract it in this case? So you look at the highest magnitude that can be represented. In this case, the highest magnitude would be 16. So 16 minus 7, that will give you 9. Right? And so you'll get exactly the same answer. Number 4, the power of 2 here is really the number of bits in the magnitude. Right? 2 raised to that number is the highest magnitude I can represent on the number line. And since I have, to represent the magnitude, I've thrown away 1 bit, which was the sign bit. So it's the total number of bits minus 1. So both ways we get minus 9. Okay. So we have already covered this in last class, but this was kind of like reinforcing what we did in last class so that you understand exactly how 2's complement works. And we also looked at some simple ways of getting the magnitude of negative numbers. Okay. Is this clear to everybody? If so, let us try to answer this quiz question. Okay. So please write down in your notebooks what you think the answer to this is. Here I have specified the number of bits. We are going to use 8 bits and we are going to use 2's complement representation. The number I want to represent is minus 32. Okay, and let me tell you that we are going to use this answer for the subsequent quiz, which will be in another 15 minutes. So please, pay attention to getting this answer correct. So now please swap your copies with your neighbors. I want everybody to swap your copy with your neighbors and check whether both of you have got the same answer. If not, try to convince each other. So unlike in the last time where we had a possibility of 2 different ways of representing the signed integer, sign magnitude and 2's complement, this we have specified clearly that it should be in 2's complement. Okay. So in how many cases, 2 neighbors have different answers? Okay, lots of cases. Okay, good. So let's ask there. Yeah. So what is your answer?
1 1 0 and 5 times 1.
1 1 0 and
5 times 1.
5 times. Okay. 1 2 3 4 5. 1 1 0 and 5 times 1. And what is your neighbor's answer?
1 and 5 times 0.
1 and 5 times 0. No, but it has to be an 8-bit representation.
Yes, I don't know.
So 1 and 5 times 0 is not even 8 bits. So can you add 2 bits and tell us what it would be? I mean, you have given me 6 bits.
Yes.
So what happened to the other 2 bits?
I don't know. No idea.
Okay. So there is another pair here whose numbers. Now we have reconciled, is it?
Yeah.
And who was correct and who was wrong?
He was correct.
So can you tell us what mistake you made?
I represented only 7 bits, same as this, so that's why.
So as 7 bits, what is the representation that you get?
Means 1 1 and 5 times 0, so that's why.
1 1 and 5 times 0.
So I forgot to add 1 1 before that, so that was the mistake.
Okay. Any other pairs whose number right over there? Okay.
Mine is 1 1 0 1 and then 4 times 0.
1 1 0 1 and then
4 times 0.
okay versus
1 1 0 and then 5 times 1.
5 times 1. Okay. So whose answer is 1 1 0 1 4 times 0? So can you explain the rationale behind that?
Actually, I converted positive 31 into binary. That came out to be 1 0, then 4 times 1. It is in 6 bits. So I converted it into 7 bits by including a 0 in the starting. Then I like switched ones into 0 and zeros into ones and added a 1 in the starting.
Now you agree that what? This is the correct answer? Yes, I'm asking you.
I agree with 31.
Oh, so you agree that his answer is
Yes.
right and your answer was wrong.
Yes, sir.
Okay. And your answer was this, right? This was your answer. And this is wrong. Okay. So why do you think this is wrong?
So because I didn't consider that we have to add one at the last step.
You have to add 1 at the last step. Okay. Okay, but if you take this and if you added 1 at the last step, what would you get?
I'll have to calculate again.
No, but you just said that you agreed with his answer, right? Okay, so let me ask, I mean, does anybody here believe that this answer is wrong? 1101 zeros? You believe that the answer is wrong? Okay, so can you tell us why you think it's wrong?
Because it's not the correct answer.
No, so okay, so let me ask you, what does this represent? 1101 zeros
Plus 1, yes. 48, minus 48.
minus 48, and how did you get that?
The MSB 1 represents minus,
Yes,
and then you take the complement.
yes,
So you get 0, 1, 0 and 4 ones.
yes.
And then you convert into decimal.
So what is
whatever.
that?
That's 47.
Yes.
Yeah, and you add 1, that's 48. So it's minus 48.
Minus 48. Good. So basically to represent minus 32, the MSP has to be 1. You're left with 7 more bits, right? And using these 7 more bits, you have to represent 31 really, because you're going to add a 1 at the end in any case, right? And you represent 31 and then you flip the bits, right? Because when you actually calculate the magnitude, you flip the bits and then add 1, right? So you take the representation for 31 and then you flip the bits, 7 bits. Does that make sense? Right? Okay, so now what we'll do is we'll start with the next submodule, which is so for which we have the video lectures. Hello and welcome. In this lecture, we are going to see how floating point numbers are represented inside a computer. Here is a quick recap of the relevant topics. We have already seen the architecture of a simple computer, and in a previous lecture we also looked at how integers, both signed and unsigned, are represented in a computer. In this lecture, we are going to see how a computer internally represents floating point numbers and how in a C++ program you can declare floating point variables. Now this is a picture that we have seen earlier. This is the basic structure of our simple computer with different parts, and at any snapshot of operation of this computer you will see sequences of zeros and ones everywhere. So what we want to ask is, how do we represent numbers like 3.14 into 10 raised to minus 23 in a computer using sequences of zeros and ones. So these are called floating point numbers, numbers with fractional values, very small numbers or very large numbers that cannot be represented as integers. And what we are going to study today is, when we write a number like this, how is it that we can represent it in a computer using a sequence of zeros and ones. So let us look at this floating point number, minus 3.123 into 10 raised to minus 11. This is the quote unquote floating point in this number. Now this number, when we look at minus 3.123 into 10 raised to minus 11, this is of course written in decimal, and in this representation there are several parts and I want to highlight them. The first is the sign, this is a negative number. Then we have this 3.123, which is also called mantissa, and then we have the base, which is 10 here, and finally we have the exponent, which is minus 11 here. Now there is nothing sacrosanct about representing floating point numbers in decimal notation. We could also use binary notation, where the mantissa would be a binary representation, the exponent would be a binary representation, and the base would be 2. In this decimal representation, if I look at the mantissa 3.123, it is basically saying 3 into 10 raised to 0 plus 1 into 10 raised to minus 1 plus 2 into 10 raised to minus 2 plus 3 into 10 raised to minus 3, and of course there is a minus sign because we have the minus sign here. Now I could write a similar number in binary where I could have a minus sign. Instead of the mantissa being represented in decimal, I could represent it in binary and I could still have this radix point or floating point. The base would be 2 and the exponent, instead of being a decimal number, I could have a binary number over there. So if I look at this number represented in binary, the mantissa here is, we have of course the minus sign because it is a negative number. This one just to the left of this radix point, this is the binary radix point, this corresponds to, in an integer, the least significant bit. So here also we will multiply it by 2 raised to 0, just like the least significant bit of an integer was multiplied by 2 raised to 0. And then for the rest of it, just like here we multiplied this by 10 raised to minus 1, the 2 by 10 raised to minus 2 and 3 by 10 raised to minus 3. Here we will multiply this one by 2 raised to minus 1, the next one by 2 raised to minus 2, then 0 into 2 raised to minus 3, and finally 1 times 2 raised to minus 4. And if you do all of this calculation, you will find that this corresponds to minus 1.8125 in decimal. The exponent is once again a binary number, and this is just the way we read off integers represented in binary. So it is 1 into 2 raised to 2 plus 1 into 2 raised to 1 plus 0 times 2 raised to 0, that is 6. So this number represented in binary actually represents minus 1.8125 times 2 raised to 6 if I were to talk about the decimal representation. And this basically gives us the core idea of how floating point numbers can be represented using bits inside a computer. We are going to have a bit for the sign, we are going to have the mantissa represented as a sequence of zeros and ones, and of course we will have to agree on where to put the decimal point. The base or the radix will always be 2 since we are talking about binary representation, and we will have the exponent which will be another binary number. Now when we write mantissa, the same number can be represented in 2 different forms. For example, in decimal 0.02345 times 10 raised to 12 is the same as 2.345 times 10 raised to 10. So which of these should I take as my mantissa, 0.02345 or 2.345? So here we say that a mantissa is normalized if there is a single non-zero digit to the left of the radix point. So to the left of the radix point there must be only a single non-zero digit. So therefore this is not normalized because to its left there is 0, this is normalized, to its left there is a single non-zero digit. And the same notion of a normalized mantissa carries over even for binary representation. This is not a normalized mantissa because to the left of the radix point we have more than one non-zero digits, whereas here to the left of the radix point we have just a single non-zero digit. And here is an interesting observation that if we are representing numbers in binary, then in any case we only have zeros and ones to be used in our representation. And if we are saying that to the left of the radix point there must be a single non-zero digit, that has to be 1. So there is always a 1 on the left of the radix point in a binary representation of a floating point number where the mantissa is represented in a normalized way, and because it is always going to be 1, we need not store it, we know that it is always going to be 1, and therefore this basically gives us 1 bit of information for free. However, as you can imagine that there will be some difficulties in representing the number 0, because in the number 0 we will not find any bit which is 1 in the mantissa, but we will see how to deal with this in a couple of minutes. So floating point numbers are represented by allocating some fixed number of bits to store the mantissa in a normalized form and to store the exponent. Now of course, since you are allocating a fixed number of bits for the mantissa and the exponent, you cannot represent all real numbers, and in fact there will be gaps between real numbers that you can represent, and this is also called finite precision artifacts. Because we cannot represent all real numbers, some funny things happen. So for example, suppose I said that you have only 3 bits to represent the mantissa, and look at this floating point number in binary 0.101 times 2 raised to 111, where this is a binary exponent. This mantissa is of course not normalized, as you can see, but suppose I said that this is my binary number and I want to add 1 to it, and what would be the result? And you will see that if you have only 3 bits to represent the mantissa, you cannot really represent this exact result of adding 1 to this number. The number of bits you need in the mantissa would need to be far larger in order to represent this result exactly. And this is what we call finite precision artifacts, that there are certain numbers that we cannot represent exactly, and so we will represent them approximately. We will represent the closest number that we can using the number of bits available to represent the mantissa and exponent. Now in C++, how do we declare floating point variables? There are 2 data types called float and double. Float basically is 32 bits for representing a floating point number. 32 bits can also be thought of as 4 bytes, of which 1 bit is reserved for storing the sign of the number, 8 bits are reserved for storing the exponent, and 23 bits are reserved for storing the mantissa in the normalized form. And the approximate range of the magnitude of floating point numbers that you can represent goes from 10 raised to minus 44.85 to 10 raised to 34.83. It is an interesting exercise to actually look at the number of bits that you are using to represent the exponent and mantissa and come up with these ranges. I encourage all of you to try and do this. There is this other data type for floating point numbers called double, in which you use 64 bits or 8 bytes, 1 bit to store the sign, 11 bits for the exponent and 52 bits for the mantissa. Here you have a much larger range of magnitude, 10 raised to minus 323.3 to approximately 10 raised to 308.3. Once again, it is interesting to calculate these ranges from the knowledge of the number of bits in exponent and mantissa. And as I said, we cannot represent 0 exactly if we are trying to use normalized mantissa. So special bit patterns are reserved for 0, and not only for 0, for some other kinds of numbers like positive infinity, negative infinity, and even for things which are also called not a number, which are the result of certain operations. For example, if I try to divide 0 by 0, then I would get something which is not really a number, and in a computer this is represented by a special bit pattern which is also called not a number. And similarly, there are other special bit patterns. How do you declare variables? In C++, you put this data type keyword float, then you give the name of the variable, or you put the data type keyword double and then you give the name of the variable. How do you represent floating point constants in C++ programs? We can represent them the usual way, and in a C++ program it is not necessary for you to write the mantissa in the normalized form. When the computer stores it internally, it will store it in its normalized form. Or you could also use what is called the scientific notation, in which you specify a number, in this case 2357.2, and then you say e minus 2, the e could be small case or uppercase, and what it really represents is 2357.2 times 10 raised to minus 2. Note that when we write this in a C++ program, the base we are using is 10. So e minus 2 really means 10 raised to minus 2. Constant floating points can also be declared in a C++ program using the const qualifier, which we have already seen earlier. So for example, if I say const float pi equals 3.1415, it means that pi has a floating point value which is not going to change during program execution, and this is the value. Recall we used such constants when calculating the surface area of a tank in an earlier lecture, or I could say const double E is 2.7183. So in summary, what we studied in this lecture are binary representation of floating point numbers, and these are the components of the representation. There is a sign bit, there are certain number of bits for mantissa, which is stored in a normalized form, and there are a certain number of bits for the exponent, which could again be a positive or a negative integer, and we have seen how to declare floating point variables in C++. Thank you. Okay, so once again we have some problems to solve based on what we just saw, but before that I just want to clarify a few things. You just saw this slide in the lecture that was played out. So here if you look at 110, this is the exponent, right, and we are representing an integer in the exponent. So one could ask, is that a 2's complement representation, or it's a sign magnitude representation? Is it an unsigned integer? So clearly we cannot just represent unsigned integers in the exponent, right, because I might want to represent 2 raised to minus 31 or something. So we need a signed integer representation over here, and then the question is this a 2's complement or a sign magnitude representation? So we will see that 2's complement is the most widely used over here, and when I write 110 here, I have really ignored the leading zeros here. So it is not the case that there is a 3-bit representation, right? We have seen that exponents are usually represented by many more bits, 8 bits in float, at least 8 bits, 11 bits in double. So when I write 110 here, it really means that there are some leading zeros, and so when you interpret it as a signed integer, it means 6, and then that's what we have said here, 6. However, if somebody said artificially that we are just going to use 3 bits in the exponent and it's a signed integer representation in 2's complement, then of course 110 will not represent 6, and you know what it will represent, right? We've just seen 2's complement representation. So this is to be kept in mind when we write 110 here. There are leading zeros, so in 2's complement this will represent 6, right? Similarly, in another later one here it was 110, so in 2's, but with the leading zeros it represents 6, and then when you shift this decimal point by 2 positions, this becomes 8, and there are still leading zeros. But truly speaking, we should, when you write a floating point representation, in fact we'll just look at it in the quiz, you have to actually give the entire representation. Okay, so here is the quiz. Please pick up your pens and notebook. So we have this C++ declaration. There is a floating point scale factor, which is 1.875 times 2 raised to minus 32. Okay, and you are required to show how this is going to be represented in the computer's memory, and we have sort of recalled what we just said, that float has 32 bits, 1 sign, 8 exponent, 23 mantissa, and the bits are going to be arranged in this way. The sign bit will be at the most significant bit, then the exponent, and then the mantissa, and of course the exponent, in this particular case we are trying to represent a negative number. In fact, if you see, this was just the negative number that you did in the previous quiz, minus 32, using 8 bits, right? So you can just pick up the answer from there, and at least you've got one part of the answer, but I want you to write out the whole representation. I mean, it looks like a lot of work to write out 32 bits, but this value has been chosen specifically such that there's not much calculation to be done. So if you start working on it, you'll see that it's not a very difficult representation. Okay, so 2 to 3 minutes for you to come up with the answer. Remember also how fractional binary numbers are represented, right? 1.1101 was, this gets multiplied by 2 raised to 0, the next one by 2 raised to minus 1, 2 raised to minus 2, and so on. So those of you who are done can now swap your copies with your neighbors. Okay, so for the sign and exponent, I am sure there is nothing to discuss. We all know what it is, right? Sign is 1 because there is a negative number, and exponent is whatever the 8-bit 2's complement representation of minus 32 you did from last time. What about the mantissa? So yes, yeah, let me randomly pick up somebody. Yes, with the striped t-shirt. 1.1. 1.111. And then 19 zeros, whole bunch of zeros, whatever. Okay, so how many people got some mantissa but is different from this? Yeah, the person with the green shirt. Yeah. 3 ones and 20 zeros. Okay, so basically you're saying that this part is not there. Right? Okay. So how many of you got some mantissa which is different from both of these two? 001. I see. Did anybody get this? Okay. So the first thing in the interest of time, the first thing to note is that we have said that this part is completely redundant. On the left hand side of the radix point, it will always be 1. So in fact, we showed it in the slides, right, that it need not be stored. And in fact, why should we store it? We're just wasting 1 bit, right? So the part that we're going to store is only the part that comes after the radix point. And now there are 2 suggestions. One is 111 and then all zeros, and 111 001 and then all zeros, right? That is what you got. So 0.875, so given an integer number, you know how to convert it to binary, right? Given a decimal number, how do you convert it to binary? So it's the same thing, right? I mean, you keep multiplying by powers of 2, right? So 0.875 times what power of 2 will give you an integer. 0.875 into 2 raised to what power? You know, it's like saying if I give you the decimal number 0.132, then 0.132 into 1000 gives you 132. 0.875 into 1000 gives you 875. So 0.875 into what power of 2 gives you a number? 8, right? So if you do 0.875 into 8, you're going to get an integer. So take that integer, find its decimal representation, and into 8, you have multiplied by 2 raised to 3, so the actual number is into 2 raised to minus 3, right? So 0.875 can be written as 0.875 is 0.875 into 2 raised to 3 into 2 raised to minus 3, right? Now 0.875 into 2 raised to 3 is what? It is 7. So this is 7 into 2 raised to minus 3. How do you represent 7? 111, and 2 raised to minus 3 means shift the radix point. It's no longer a decimal point, it's a binary point now. 3 places to the left, so you get 0.111, right? So it's pretty much the same way that you convert integers to binary, except that you first have to multiply by an appropriate power of 2 to get an integer. You write down that integer in binary, and then you know exactly how many places to shift that point by. Is that clear? Okay, so I guess what we will do is, so let's quickly look at this question. So constant float, acceleration gravity is 9.875. Okay, now this is a statement in a C++ program, and this 9.875 has to be represented in the computer's memory. Okay, using, this is a float, so it's the same representation, 1 bit signed, 8 bit exponent, 23 bits mantissa, but now this is 9.875, earlier it was 1.875, 2 raised to minus 32. So we have gotten rid of that 2 raised to minus 32 or whatever over here, and instead of 1.875, it's 9.875. So now that all of you know the representation of 0.875, I hope you will be able to get the representation of 9.875, and then you have to normalize the mantissa and find out what the exponent is. So can you try this out? 9.875 is 9.875. So you represent 9 as a binary number, everything is to the left of the radix point. You represent 0.875 as a binary number, everything is to the right of the radix point. Just put the two parts together, that will give you 9.875. But now you have to represent it as a floating point number. So you have to have a mantissa which has just one bit to the left of the radix point. Okay, so now you can swap it with your neighbor. It's still a floating point number, so we have the same representation. 1 bit sign, 8 bits exponent, 23 bits mantissa. So does everybody understand what is the mantissa? You didn't get what a mantissa is. Okay, so this is a slide that we showed. You understand what this number is? I mean, what I'm trying to represent using this number? In decimal, not in binary. So it's some number times some power of 10. So this number is the mantissa and the power of 10 is the exponent. No. So there is an issue of normalized mantissa and non-normalized mantissa. But the mantissa is the part which is basically a number with which you multiply a power of the base. So for example, look at this. It's the same number represented in two different ways. For this number, this is the mantissa. 0.02345 is the mantissa. If I write it like this, 0.02345 is the mantissa. If I write it like this, 2.345 is the mantissa. So depending on how I write the number, the mantissa is either this or that. Because there are different ways to write the mantissa for the same number, therefore we want to come up with a normalized way to write the mantissa, such that for one number there is only one mantissa. And the normalized mantissa says that to the left of the point there must be exactly one digit and it must not be 0. So then this gets ruled out and we accept this. So is that clear? So whenever you write a number times base raised to something, that number is the mantissa. It may not be normalized. When you normalize it, you get a normalized mantissa. Does that answer your question?
So,
Yeah?
yeah. So I have a doubt in the conversion, like of the second normalization, second part. Like how did we do that?
So this is the mantissa. So if I look at this number, the mantissa is 110.101 and the exponent is 110, but there are really leading zeros over there. So it's, let us say, 5 leading zeros followed by 110, 8-bit exponent. So in this representation of the number, this is the mantissa, 110.101, right? However, to the left of the point, we have 3 digits here, we have 3 bits here. So therefore it is not a normalized mantissa. So we have to shift the point such that there is exactly 1 bit to the left. How do we shift the point? So this is represented in binary. So just like in decimal, when I multiply by 10, the point moves one place to the right, and when I divide by 10, the point moves one place to the left. So in binary, when I multiply by 2, the point moves one place to the left, to the right, and when I divide by 2, the point moves one place to the left. So in order to get this point here, I'll have to bring it 2 places to the left, right, which means I have to divide it by 2 squared, right? But then if I have divided by 2 squared, I should also multiply it by 2 squared such that these factors cancel out. And if I multiply by 2 squared, so this is already 2 raised to 6 times 2 squared, which is 2 raised to 8, and that's what is represented here, right? As I said, there are leading zeros here which have been ignored just to keep the representation clutter free. Is that clear? Okay, so we'll stop here.